Greetings everyone and welcome back to our online lecture series for CHE 2300. In today's lecture video we are going to begin discussing different types of heat exchanger equipment. Primarily for this course we will focus on shell and tube heat exchangers since those are the most common type of heat exchanger you will run into in the chemical industry, but you will also be introduced to a number of different types of heat exchangers. Alright, let's jump into it. We have three major types of heat exchangers. The first one of those are regenerators. In regenerators, I have a hot and cold fluid. They are alternately flowing through the same space with physical mixing. What I mean by that is that, let's say I have a tube. I flow hot air into that tube by itself. I heat up the tube with that hot air, and then afterwards I flow in another fluid and use that hot or heated tube to then heat the cool air that I'm flowing in afterwards. And I do this in an alternate fashion to be able to heat a particular stream. We won't focus too much on regenerators because, as I say down here, regenerators are typically used in electrical power generation. Right, so not often are we going to be dealing too much with regenerators. We're going to spend our time focused on 2 and 3, and really we're going to spend our time down here focused on 3. Okay, so the other two types of heat exchangers are open and closed heat exchangers. Number 2, we're going to talk about open type heat exchangers. In these type heat exchangers, we have physical mixing of the hot and cold fluid. So I have two fluids that come into my heat exchanger. They physically mix with each other, and then I have a single exit stream of my fluid. This could be helpful if I had hot and cold water. I wanted to mix them together to heat up my water stream, so it doesn't bother me necessarily that the two fluids are intermixing with each other. More often than not, and the most common type of heat exchanger you will run into in the chemical industry is what's referred to as a closed type heat exchanger. For these types of heat exchangers, the hot and the cold streams are physically separated from each other. So here I say that they are passed around each other without physical mixing. Right? And so this, again, is the most common type of heat exchanger you will run into. And when we talk about shell and tube heat exchangers, that's what we're referring to here, a closed type heat exchanger. We have seen an example already of a double pipe heat exchanger with the example problem of the water and benzene. That is a closed type heat exchanger because the benzene and the water stream never physically mix with each other. Right? They're separated by the wall of that inner pipe. Okay, so in this picture I have a double pipe heat exchanger. What I have here is a cold fluid. My cold fluid enters from the left-hand side. That cold fluid flows through the inner pipe, never physically mixing with the fluid on the outside, and comes out on the right-hand side of the screen. What I see here with my hot stream is I have my hot stream, in this case, coming in from the top. Hot stream comes and fills in this outer area of my double pipe heat exchanger and then flows out the bottom. Right, so I have my THA, THB, TCA, TCB, where A and B are simply the entrance and exits of my heat exchanger respectively. I'm going to highlight this again so that we are all on the same page. And I think if I keep saying this, keep pounding it, it's going to eventually stick into your head. Heat transfer, or the heat transfer process that typically occurs, is we have convection from the hot fluid to the outside surface of the inner pipe. That, again, is described by Newton's law of cooling, which is related by some convective heat transfer coefficient. Again, the convection part comes from the fact that the fluid is moving, whether it is forced convection, meaning that we pumped that fluid or we moved that fluid through some pump or some fan, or it's through natural convection, which is caused by gradients in the density, which are caused by gradients in the temperature. In either case, heat transfer from convection can be described by Newton's law of cooling. Once we have convection from the hot fluid to the outer surface of the inner pipe, again, we're describing this example above here. We may have a case where we have the hot fluid inside the pipe. Right? That's typically not the case, but I do want to point that out. So convection from the hot fluid to the outside surface. Then we have conduction through the pipe wall. We saw early on that conduction was described by Fourier's law. After we have conduction through that pipe wall, we then have convection from the inner surface of the inner pipe to the cold fluid. So convection from the hot fluid to the outer surface, conduction through the pipe wall, and then convection from the inner surface to the inner cold fluid. Again, that convection to that cold fluid we can describe using Newton's law of cooling. Don't want to be redundant here, but I'm going to be redundant here. Convection occurs at a surface, so to or from. That's what we just saw. Convection from the hot fluid to the surface, and then convection from the surface to the cold fluid. And conduction occurs through a material or a fluid. And again, keep in mind when I'm using dimensionless numbers for convective heat transfer, like the Nusselt number or the Prandtl number, the parameters in those dimensionless numbers are for the fluid. Right? So the thermoconductivity, the specific heat, the viscosity, all of those are for the fluid, right? Not for the material such as the steel pipe. Right? We need to use conduction equations to describe that, and that's again where Fourier's law comes into play. Okay, so what we haven't talked about so far, so we have seen an example of a double pipe heat exchanger. More specifically, what you are observing here in this double pipe heat exchanger is what is known as a single pass heat exchanger, meaning that the hot fluid and the cold fluid only make one pass through that heat exchanger. Okay, excuse me. So, I do want to highlight this right now. I'm going to take a second for the exam that is coming up on Thursday. The exam will cover everything back to flow through packed beds and fluidized beds, all the way up to everything you see in this lecture. However, it will only deal with single pass heat exchangers. So you may have to solve a shell and tube heat exchanger problem, which we'll go through an example at the end of this lecture, but it will only be a single pass unit. In the next lectures moving forward, we will deal with and understand the concepts used, and the equations used to describe heat transfer when I have a multi-pass heat exchanger. So again, we're only talking about a single pass heat exchanger, you will only be asked to solve problems for a single pass heat exchanger. But conceptually, everything from these notes is fair game for the exam on Thursday. Meaning I might ask a conceptual question about a multi-pass heat exchanger, but I will not ask you to solve any analytical problems regarding or related to multi-pass heat exchangers. We will keep that restricted to double pipe or single pass shell and tube heat exchangers. Okay, this was mentioned in this double pipe heat exchanger problem, but our heat exchangers have different flow configurations that they can be operated in. They can be operated in co-current, or also known as parallel flow. In this case, both the hot and the cold streams are flowing in the same direction. We can have what is called countercurrent flow, which is what we saw in the double pipe heat exchanger. In that case, we have the hot and the cold fluid flowing in different directions from each other. And then we can also have what is known as cross flow. the streams flow across each other and generally remain unmixed. And so a good example of that is the following, figure 2. This is what is known as a cross-flow heat exchanger. And here, let's say you might have some hot air, and that is being used to heat a stream of, I don't know, carbon dioxide. All right, so I'm flowing my hot air. It is remaining unmixed, meaning the air and the CO2 are not physically mixing with each other, but I'm still using that hot air to heat my colder CO2 stream. So we have 3 types of flow or configurations for shell and tube heat exchangers, double pipe heat exchangers. This is where we will primarily focus our effort, talking about co-current and countercurrent. But I do want you to recognize or at least understand that there are heat exchangers that operate in a cross-flow configuration. To get as much heat transfer area as possible into a minimal space, it is common to use what we refer to as a shell and tube heat exchanger. On the following page, I am showing a picture of a shell and tube heat exchanger. And before I talk about the flow configuration of this heat exchanger, I do want to introduce some terminology. So we have 4 important parts of this shell and tube heat exchanger. The first one is the shell. Right? And the shell is simply this outer shell that I'm highlighting in green. Let's change our colors up. Next thing we have are the tubes. I'm not going to highlight them all. Of course, I'll highlight one here. This would be one of the tubes in the shell and tube heat exchanger. Okay, go to another color. Let's do a black. The next thing we have are baffles. Right? And what the baffles do, we'll talk about in a second. I don't want to get into that too much here, but let me just draw a couple of these baffles. And the purpose of the baffles, we will see in a moment, is to direct flow. All right, the final thing I'm going to introduce, and I will use let's use orange for this, are the tube sheets. And the tube sheets can be seen here. Right? And these tube sheets are simply there to physically hold the tubes in place. Okay. So, let's talk about what is going on here. Let's imagine the following scenario where we have a cold stream. So let's say we have our cooling water coming in here. It is leaving there at the top on the left. Then we have an incoming hot stream coming in from the top right and exiting in the bottom left. So what you will see here is an example of a multipass heat exchanger. It is multipass because when my cold fluid comes in, wrong color. When my cold fluid enters my heat exchanger, it goes inside my tubes. It is forced inside those tubes by these tube sheets that are holding the tubes in place. It then flows through the heat exchanger. I'm just going to follow one stream. Comes out, turns back around, and flows through another set of tubes in the heat exchanger before actually exiting the heat exchanger. So this would be an example of what is called a double pass shell and tube heat exchanger. Again, a double pass because both, you'll see in a second, the hot and cold fluids make two passes through the heat exchanger. So double pass shell and tube heat exchanger. In the case of my hot fluid, well, I should take that back. In this example, the double pass is coming from the fact that the cold fluid is making two passes through the heat exchanger. Technically, what you'll see is the hot fluid is not making two passes. It is just having its flow directed in a different manner based on these baffles. And so the purpose of these baffles is to direct the hot fluid, to direct the flow of the hot fluid within my shell and tube heat exchanger. So again, remember in black I have my baffles, and so what happens is that my hot fluid comes in. It cannot flow to the left because of the baffle right there, so it has to flow all the way down across those cold tubes and then back up around, passing over those cold tubes again, and then it does this snake-like pattern through my shell and tube heat exchanger, passing over those cold tubes multiple times before it exits out the other side of my heat exchanger. Right? And so this is why shell and tube heat exchangers are so popular, because I can get high heat transfer in such a small amount of space because I can use things like multiple passes and also these baffles to direct the flow of the hot fluid. Therefore, the hot and cold fluid, even though they're not physically mixing, right, they are in contact with each other through those pipe walls for a longer period of time, therefore allowing for more heat transfer to occur. Okay, so this is what I just said up there. This is called a double pass heat exchanger because the cold fluid makes two passes. Here we're going to call that the tube side. This is let's just keep our colors consistent here. So our tube side fluid makes two passes. This is our cold fluid. And then we have our shell side fluid making only one pass. That is our hot fluid. And so then I pose this question down here. Which fluid should be in the tube side? Or vice versa, which fluid should be in the shell side, and why? Okay, and the answer to that really comes down to the properties of the fluids themselves. So, for these shell and tube heat exchangers, it is much easier to replace a couple of tubes in that shell and tube heat exchanger, right? I open up the heat exchanger, I can physically remove a single tube, or I can remove multiple tubes if I need to. It is a lot harder to replace the shell part of the heat exchanger. There's a lot more work that goes into replacing the entire shell of the heat exchanger than goes into replacing individual tubes within that heat exchanger. And so we haven't talked about it yet, but we will in a couple lectures, this idea of fouling. And so fouling occurs in the heat exchanger. And the simplest way to think about fouling is that we have some buildup of material that, we have a deposit of material on the surface of our pipe, both on the inside and the outside. And that deposit builds up as a film. And as we saw in previous lectures, right, the overall temperature drop is simply or the overall temperature drop is related to the individual resistances over which that temperature drop occurs. And so what happens is that we treat fouling just like another thickness within our heat exchange equation. But we'll talk more about fouling in a little bit. The point I wanted to make here is that because it is easier to replace the tubes within the shell and tube heat exchanger, we should always be passing the, what we'll say, dirtier fluid through the tubes, because more fouling is going to occur inside the tubes, and therefore it will be easier for me to replace a single tube than it would be for me to replace the entire shell. And so typically the cooling fluid, right, more often than not, when you have these large chemical plants, you'll find them next to some source of water. Maybe that's a lake, maybe that's actually on the coast, something like that. And so what happens is they're pulling their cooling water from that lake or stream or river, or if they're on the coast, from the ocean. And that water is usually not being processed before it's fed into the heat exchange equipment, meaning that it is dirty water. And you will end up with fouling occurring inside your heat exchanger. And so, if my water is dirty, compared to whatever fluid I am trying to cool, then I would flow that through the tube side of my heat exchanger. But again, as a general rule of thumb, I'm just going to look at my two fluids and ask myself which one of these is the quote-unquote dirtier fluid. Which one will I have to worry about fouling more often? And therefore, if I do, let's say fluid A, I have fluid A and fluid B. If fluid A is the dirtier one, that's the one I'm sending through the tube side of my shell and tube heat exchanger in general. Okay, enough about that. Let's keep moving on. The following figure shows both parallel or co-current and countercurrent heat exchangers. So again, parallel or co-current means that I have both my hot and cold fluids coming in on the same side of my heat exchanger and exiting on the opposite side of my heat exchanger. For countercurrent flow, which is what we saw with our benzene and water example, we have our hot fluid entering the heat exchanger on one side, and we have our cool fluid entering the heat exchanger on the other side. What you will see here, hopefully, is that neither one of these profiles is linear. Right? Meaning that the temperature difference between those streams, or the driving force for heat transfer, is not constant throughout my heat exchanger. This is why we use a log mean temperature difference when describing the temperature drop between our approach streams. So our approach temperatures, let me clear this out. This is one approach temperature difference. This is the other approach temperature difference. Right? And again, when I say approach temperature, I'm simply referring to the temperature difference between the two streams on either side of the heat exchanger. So in the case of parallel flow, we're talking about the temperature difference between the entering cold and hot fluids. And in the case of countercurrent flow, we're talking about the temperature difference between, let's just look at this one side, the temperature difference between the hot fluid in and the cold fluid out. So hopefully also, as you can see, that this type of heat exchanger is going to give me more uniform heat exchange throughout the entire length of my heat exchanger, because this driving force or temperature difference is very similar throughout the entire heat exchanger. Where here I have a large temperature driving force at the entrance of my heat exchanger, but then a very small temperature driving force at the exit temperature of my heat exchanger. Okay, another interesting thing to point out is you might ask yourself here, well, why would I ever operate over here in countercurrent flow, or excuse me, in parallel flow, if my better heat exchange is going to occur with countercurrent flow heat exchanger? And one of the best examples or things to keep in mind here is, let's imagine that downstream from this heat exchanger, right, we have some reactor. And we are feeding in this cold fluid out into that reactor. But our reaction is very, very temperature sensitive, and if that temperature of the cold stream goes above a certain temperature, we end up causing a runaway reaction in our reactor, and we have a catastrophic failure at our plant. If we operate in parallel flow, what you can see is that the temperature of this cold fluid will never be hotter than the temperature of our exit fluid. So we can put in a safety control based on the flow configuration of our heat exchanger. We will never, ever, ever, ever be able to create a cold stream temperature on the outlet side that is hotter than the hot stream temperature on the outlet side. Right? If I move over to countercurrent flow, you can see that that is definitely not the case. The cold fluid that is leaving my heat exchanger is definitely at a higher temperature than the hot fluid that is leaving my heat exchanger. Right? So parallel flow configuration does have its place in the chemical industry. And one of the main examples of that is being able to directly control or limit the temperature of that cold stream leaving the heat exchanger by whatever the hot stream is that leaves the heat exchanger, because that cold stream temperature can never be hotter or higher than the temperature of the hot stream that is leaving the heat exchanger. On the bottom, you are seeing examples of an evaporator and a condenser. Here, let's take my evaporator for example. I have a hot fluid that is entering my evaporator. On the left-hand side, it is exiting on the right-hand side, and then I have my cold fluid here, and I do not have a direction. Right? There's no arrow here. And if you look over on the condenser side, right, I have the exact same thing. So here I have some hot vapor that is condensing, and here I have some cool fluid that is evaporating. Right? Why do I not have directions on either one of those? Well, these are temperature profiles for single pass double pipe heat exchangers. We in this class will usually assume some adiabatic process, meaning that all of the temperature or energy that leaves the hot stream goes into heating the cold stream. For a simple double pipe condenser or evaporator, the flow direction of the fluid changing phase is not important. Right? It's not important because that fluid remains at a constant temperature. Meaning that regardless, let's look here at the evaporator, regardless of what direction that cold fluid enters, the approach temperatures on either side of my heat exchanger remain exactly the same. Because the cold fluid does not change temperatures. Same thing over here in the condenser. It doesn't matter what direction I flow my hot fluid, because the approach temperature on the left-hand side of my heat exchanger is going to be exactly the same, regardless of what direction that hot fluid enters. Okay, so on the next page, right, I'm giving you some examples of heat exchangers where we have both sensible and latent heat exchanged. We're not going to talk too much about that at this moment, but I do just want you to see, right, there are different temperature profiles that occur where maybe I have some superheated stream that comes down and cools. It then condenses with no temperature change, which is what we saw in the example above, and then we have some cooling of that condensed vapor. Right, so those are examples or profiles for heat exchangers where both sensible and latent heat are being transferred. Okay, so let's talk about some basic equations for heat exchangers. If we consider the temperature distributions in both a countercurrent and co-current heat exchanger, doesn't really matter. Let's focus on this top one. So again, what we have here is we have our approach temperature on the left-hand side of the heat exchanger, which we're calling delta T1, and we have our approach temperature on the right-hand side of the heat exchanger that we are calling delta T2. Right, same thing over here with our co-current heat exchanger. We have our approach temperature delta T1 on the left-hand side, the approach temperature delta T2 on the right-hand side. So what about the scenario where delta T2 equals 0? Right, getting this to equal 0, meaning the temperature of the hot stream and the cold stream are exactly the same. Is that possible? Yes, theoretically. If I make my heat exchanger infinitely long, or I have an infinite amount of heat exchange surface area, then yes, theoretically, those approach temperatures will eventually, or that approach temperature will eventually become 0. Practically, can we do that? Absolutely not. Right? There is no way we can get those two temperatures to equal each other. Right? If I'm going to throw out a number, I would say, general approach temperatures, if we're talking about here on this side, is somewhere in the range of, the best we can get is, let's say, 5 degrees Celsius, 10 degrees Celsius, somewhere in that range. Right? But there's no way we are getting those two streams to actually equal each other when they leave the heat exchanger. Okay, so what I'm going to introduce here, what I'm going to introduce here is what we will refer to as the heat exchanger design equation. And this heat exchanger design equation is going to allow me to calculate things like the total amount of heat flow in my heat exchanger, or maybe the total amount of required surface area for a particular heat exchanger to operate properly. And so the total heat flow in our heat exchanger is described by the overall heat transfer coefficient multiplied by the total area of heat transfer. And what I mean by total area is if I come up to this example here of my double pipe or double pass shell and tube heat exchanger, the entire outside surface area of heat exchange would need to be the entire outside surface area of that one pipe multiplied by 6, because I have 6 tubes inside my heat exchanger. So that total area is giving you the total amount of required heat transfer area for a particular scenario. Heat flow equals overall heat transfer coefficient times the total area multiplied by the log mean temperature difference, where in this case our log mean temperature difference in terms of delta T1s and delta T2s is equal to delta T2 minus delta T1 divided by the natural log of the ratio of those two approach temperatures. Okay, so this is our heat exchanger design equation. And again, it allows us to calculate things like the total amount of heat transferred or the total amount or total required heat transfer area. Okay, I just said that. UA assumptions. We are going to assume that overall heat transfer is constant across the entire heat exchanger, i.e. it is not a function of the temperature difference between the hot and cold streams. And then we're going to assume that the specific heats of our fluids are constant. So if I look at this equation, going too far. If I look at this equation, what happens when delta T1 equals delta T2? Meaning the approach temperature on the left-hand side of my heat exchanger is equal to the approach temperatures on the left-hand side of my heat exchanger. I would end up with a scenario of 0 over 0. And therefore, it would tell me that I have no temperature difference, right? Everything is 0. I shouldn't have any heat transfer. We, of course, know that's not the case. So if we dig deep here, we're going to recall L'Hopital's rule, which is going to allow us to calculate that equation when we have the case of delta T1 and delta T2 being equal to each other. So, in the limit where delta T2 is approaching delta T1, for this particular equation, delta T2 minus delta T1 divided by the natural log of the two. Okay, let me recast that parameter. So we'll call it F as F approaches 1 for the equation of delta T1 minus times F minus 1 divided by the natural log of F. Right, what you would see here is you would end up with the following equation. Here, F is equal to delta T2 divided by delta T1. So again, 0 over 0, that's undetermined. So we need to do a bit of manipulation to our equation. What L'Hopital's rule tells us is we take the derivative or differentiate the numerator, differentiate the differentiate the numerator, then differentiate the denominator with respect to our term F. When we do that, we end up with the following equation for our design equation, because what you end up with is that simply the log mean temperature difference is either delta T1 or delta T2. It doesn't matter, right? At the end of the day, this also equals delta T2 because we know that delta T1 and delta T2 equal each other. So I could just as easily put a delta T2 term here as well. But for the case where my approach temperatures on both sides of the heat exchanger are equal to each other, I have this, I guess you could call, more simplified design equation that is just a function of the temperature difference on one side of my heat exchanger. In that previous example, we assumed a constant overall heat transfer coefficient. However, you'll find that that heat transfer coefficient can vary with temperature. So let's make the assumption where we have U varying linearly with the temperature drop that occurs inside my heat exchanger. In that case, my design equation would take the following form. So the total amount of heat transfer, total heat flow, is equal to my total area of heat transfer. And now this is multiplied by an overall heat transfer coefficient on one side of the heat exchanger multiplied by delta T1 minus my heat transfer coefficient on the other side of the heat exchanger multiplied by delta T2. And then all of that is divided by the natural log of the ratio of those two terms. Again, This is for the case where U varies linearly with temperature. More often than not, we're just going to assume that the overall heat transfer coefficient is constant, but in the case where you're told, hey, it varies linearly with temperature, here are the two values of the overall heat transfer coefficients on either side of the heat exchanger. This would be the equation to use to solve for things like, again, the total heat flow or the total heat transfer area required. Okay, so let's keep moving along. Other than shell and tube heat exchangers, what other type of heat exchangers might I run into in the chemical industry? Okay, the first one of those is a spiral heat exchanger. Hard to see here, but what I have, since I can draw in color, is I have some hot fluid in one part of the spiral, and then I have my cold fluid in the other part, and these alternate, right? Then I would have a cold fluid here, and then my hot fluids in between. What are some of the advantages? What are some of the advantages of a spiral heat exchanger? Right, they have high thermal efficiencies, compact designs, much like a shell and tube heat exchanger. Right, one of the biggest benefits of spiral heat exchangers is that they are ideal for slurries or fluids with suspended solids. Right, so if I had a slurry or a fluid with suspended solids, some type of colloidal solution, I more than likely wouldn't put that through a shell and tube heat exchanger. I would use a spiral heat exchanger. And just to give you an idea of how large these heat exchangers can be, right, assuming this person is 6 feet tall, right, as you can see, that heat exchanger is about 10 feet tall. Right, so these things can become extremely large when you get to larger chemical plants. Okay, spiral heat exchanger. The next heat exchanger that I want to introduce to you, other than the shell and tube heat exchanger, is what is known as the plate heat exchanger. So for a plate heat exchanger, what you have is it uses metal plates to transfer energy between two fluids. These metal plates are typically corrugated, meaning that they have some type of alternating ridges or grooves in them. And these ridges and grooves, what they do is they cause the flow to become turbulent. And we all know that the heat transfer coefficient is directly related to the Reynolds number. The higher the Reynolds number, the higher my heat transfer. So I want to be operating in the turbulent regime if I can. This type of heat exchanger allows fluid to see a much larger surface area than a conventional heat exchanger. And that's one of the biggest benefits of these type of heat exchangers, is that it has a large surface area over which heat transfer occurs. Right? These type of heat exchangers are also nice because it's easy to it's easy to remove and clean these plates. We can also easily expand this heat exchanger by adding more plates to it. And so in this particular example, what you might have is you would have a hot fluid flowing on one side, and then on this other side you would have your cold fluid. Right? And so the heat exchange is exactly the same as the other type of heat exchangers. Right? We have convection from the hot fluid to the metal surface, conduction through that metal surface, and then convection from that surface to our colder fluid. Down at the bottom, I am showing you again a picture from what a plate heat exchanger might look like when you get out into industry, much like you saw with the spiral heat exchanger. Right? Assuming this person is 6 feet, that heat exchanger is about 10 feet tall. Right? And you can see, if I look down the thickness of it, there are many, many, many plates that are stacked on top of each other. Right? And also, as you can see, this person is adding a plate. We can add as many plates as we need So again, this is why it has this benefit of being expandable. Right? If I have a shell and tube heat exchanger, right, I already have my tube sheets. My tube sheets define what type of pattern I have. Right? So if that's the size of my tube sheets are already going to have holes cut in them. Meaning that I cannot add more than 10 tubes to this heat exchanger. If I wanted to, I would need to change this tube sheet on both sides of my heat exchanger, and I would more than likely have to also change the baffles in my heat exchanger. So expanding a shell and tube heat exchanger is not straightforward at all. And so that's one of the benefits that a plate heat exchanger provides, is that we can simply add more plates to that heat exchanger, thus expanding our area of heat transfer and allowing our hot fluid and cold fluid to be in contact with each other for a longer period of time. Okay, let's do an example problem. Summarize everything we have seen in this lecture. For this example problem, we have a single pass shell and tube heat exchanger. Shown in the schematic, we have oil that enters our heat exchanger at 375 degrees K. It leaves degrees K. It's 375 K. Kelvin is not, don't need degrees on that. It leaves our heat exchanger at 350 K. And we have cooling water coming in on the left-hand side. So this heat exchanger is, of course, operating under countercurrent flow. And we do not know the exit temperature of that water. Let's define some parameters. Let me switch my colors here. We are going to let the overall heat transfer coefficient be equal to 250 watts per meter squared Kelvin. The CP of our oil we will set at 2090 joules per kilogram Kelvin. The mass flow rate of the oil in our heat exchanger is 0.6 kilograms per second. The CP of the water is equal to 4,177 joules per kilogram Kelvin, and the mass flow rate of our water is 0.2 kilograms per second. Nope, I don't need that. I already changed it, so this is just kilograms per second. We are asked in this problem to calculate the total heat transfer area required for this particular process. Down here at the bottom, it says you may assume the heat exchanger operates adiabatically. So I can go to my overall design equation, which tells me that the heat flow, the total heat flow, is equal to the overall heat transfer coefficient multiplied by that total area of heat transfer, and that is multiplied by the log mean temperature difference. So the first issue that we run into here is that we do not know the exit temperature of the water, and so we therefore cannot calculate this log mean temperature difference. However, what we can calculate based on the temperature drop of our oil and using an energy balance, we can calculate that exit temperature of our cold fluid. Once we know the exit temperature of our cold fluid, we can calculate the log mean temperature difference within that heat exchanger, and then we can use that to calculate the total heat transfer area required for that process to occur. So let's do that. the first thing we're going to do is we're going to say that the heat transferred to the water is equal to the negative of the heat transferred from the oil. I'm just going to switch the temperature difference around so I get rid of that negative. So I know that negative, well, no, let me just switch my temperature difference around. So M dot Cp oil times the temperature of the oil entering, temperature of the oil leaving. Right, that gets rid of my negative. And that is equal to the mass flow rate of my water. Let me write oil over here. Times the Cp of my water multiplied by the temperature difference of the cold fluid leaving and the temperature difference of the cold fluid entering. Okay, we know all parameters in that equation except TCB, which is what we are solving for. So let me plug in my numbers. 0.6 kilograms per second. 2090 joules per kilogram K. Here I have 375 Kelvin minus 350 Kelvin. That is equal to the mass flow rate of water, which we know to be 0.2 kilograms per second. We're going to multiply that by 4,177. I'm not going to write my units so that I can stay here without having to zoom out anymore. And then I have my temperature difference of TCB minus 280 Kelvin. So if I've done my math correctly, I should end up with an exit temperature of around 318 Kelvin. So this number here, we can erase that. We now know what that is. That is 318 Kelvin. Knowing the exit temperature of the water, we can now calculate the log mean temperature difference, which again is just going to be that delta T2 minus delta T1, where here, right, we can define that as being our delta T1. This is going to be our delta T1. Well, let me draw it right at there. There's our delta T1. And then this difference here is going to be our delta T2. So delta T2 minus delta T1 divided by the natural log of those quantities. If I do my math there, plug in my numbers, I end up with a log mean temperature difference of 63.3 Kelvin. Now that I know my log mean temperature difference, I can come back up to my equation and calculate the total area of heat transfer, because again, I also know this value. Right? I just determined that. So I can take that value from my energy balance above. That goes into my heat flow. I know what my overall heat transfer coefficient is because I'm given that with my problem. I'm asked to calculate A sub T, and I just calculated my log mean temperature difference. So let me plug in those numbers. For my total heat flow, I have 31,350 joules per second. That is equal to 250 joules per second meters squared Kelvin. Right, this is my watt. That is multiplied by the total area of heat transfer, and then I have my log mean temperature difference, which is 63.3 Kelvin. if I've done my math correctly, I end up with a total area of heat transfer right around 1.98 meters squared. Okay, so hopefully that example problem gave you a bit of an idea of what type of problems we may be solving when we're using our heat exchanger design equation.